Let's continue to talk about acid-base equilibrium. By the end of this model, you will be able to calculate Kb for a weak base given its concentration and the pH of the solution, and vice versa. Also, you will be able to calculate the pH of a weak base or its percent ionization given its concentration and Kb. You will calculate Kb, or the base dissociation constant for a weak base given the acid dissociation constant of its conjugate acid, and similarly calculate Ka from Kb. You will be able to predict whether an aqueous solution of a salt will be acidic, basic, or neutral. We'll practice the relative strength of a series of acids from their molecular structure. And finally, you will define and identify Lewis acid and bases. So, what is a weak base? Ammonia, NH3, is a weak base. Like weak acids, weak bases have an equilibrium constant called the base dissociation constant. This is Kb. The equilibrium calculation worked the same as for acid, using the base dissociation constant instead. So here we have ammonia in water producing NH4 plus hydroxide anion. So the equilibrium constant of Kb for this equation will be the products of the reactant. Remember that the water is a pure liquid, so it's not part of the expression of Kb. So it will be the products of the concentration of the product divided by the concentration of NH3. So that's Kb. Kb, the products of the concentration of the products divided by NH3. The base dissociation constants. Here we have different examples of different weak bases, as we can determine or we can see that basically when we talk about dissociation constant acid or bases, the dissociation constant are for the weak acid or bases. Remember that the strong acid or bases, they dissociated completely. So you're not going to find any Ka or Kb for strong acid because they're completely dissociated. In solution, you're going to have 100% of the products of that neutralization or dissociation. So here, as the same as Ka, as higher the Ka, stronger is that weak base. So let's do an example. What is the pH of 0.50 molar NH3? Remember, NH3 is a weak base, okay? So for bases, usually we determine the pOH, but then from the pOH, we can calculate the pH, okay? So NH3 plus water is in equilibrium producing NH4 plus OH. That's what I mentioned that we calculate the pOH because in this solution, we don't have H positive, we have OH. So we calculate the concentration of OH. From this one, we can calculate the pOH by using the formula of pOH minus log of the concentration of OH, and then we can calculate eventually the pH with the formula of pH plus pOH equals 14. So the Kb expression, as we mentioned before, is this one, and for ammonia, the Kb is 1.8 times 10 power minus 5. And we create the table again as we did it with the weak acid. The initial concentration 0.15 for this one. We don't have nothing from of NH4OH. And the change, we don't know what is a change for each one, but we know that we can use a variable that is X for NH3 because as a reactant we use the minus. NH4 and OH, they are products, so that's why the change is positive. And at equilibrium, this will be the expression of NH3 will be 0.50 minus X, and the expression for NH4 and OH will be X. So that means that if we determine X, we're going to find also the concentration of OH because X represents the concentration of OH at equilibrium. So by having X, we determine the pOH and then the pH. So the expression, once again here, this is the KB equals to x2 divided by 0.15 minus x. These are the expression at equilibrium for the products and for the reactant. We assume the same thing, that this value, the x is pretty small. So we simplify this part and divide x2 over 0.15. Okay, so we eliminate this x by assuming that the x is really small. And then we basically do the same thing as before. Rearrange this equation and obtain the x, that is 1.6 times 10 power of minus 3. This value, remember that this x is equal to the concentration of OH. Okay, so we can calculate from here 1.6 the POH, that will be 2.80. When we apply the minus log to this value is 2.80, and then we can subtract 14 minus this and calculate the pH. Because remember that POH plus pH is equal to 14. And if we have the POH, we can calculate the pH, that in this case is 11.2. So for a solution of 0.1 molar of NH3, we have a pH of 11.2. We have different types of weak bases. Two main categories are the neutral substances with an atom that has a non-bonding pair of electrons that can accept protons. This is like ammonia and the amines. So in this case, we have species that they just bind, okay, the proton because they have non-bonding pair of electrons available. Most of the time, it's compounds with nitrogen. Nitrogen has a lone pair, okay, that can um, attract or can you can bind there a hydrogen, a proton. So all those nitrogens species basically are weak bases. And anions of weak acids, also they are weak bases. Remember that when we have a weak acid and it dissociated, it produces a conjugated base. So those conjugated base are also weak bases, anions, okay? The anion of those weak acids. The relationship between Ka and Kb, here we have some conjugated acid-base pairs. And for a conjugated acid-base pair, Ka and Kb are related in this way. Ka times Kb is equal to Kw. Okay, so if we have one of this, we can calculate the other one because the Kw, the value for this one is 1.0 times 10 of minus 14. So if we want to have if you know one of them, you can calculate the other one. So Kw divided by Ka is equal to Kb, or Kw divided by Kb is equal to Ka. So you can rearrange this equation to obtain Ka or Kb by dividing to Kw. So let's talk about the acid-base properties of salts. First, let's review this equilibrium between acetic acid and water. When these two react, it will produce H3O positive and the ion of acetate. With the remember that in equilibrium, we're going to have all four substances in the beaker or whatever this is taking place. Okay, so we're going to have the acetic acid, water, H3O positive, and acetate. All of them are going to be in that place. So with the concentration of H3O, we can determine the pH of the whole solution. Okay, so we can calculate this concentration and this will dictate the pH of the solution. Now, the other product that is formed is known to be a salt. Okay, so this one is a salt and also is an ion. This ion is negative, so it's an anion. So from a weak acid, you're producing an anion, a salt that is an anion. If we have the other reaction that is NH3, that is a base, plus water, when NH3 react with water, the NH3 will remove a hydrogen from water and produce NH4, and from this you will have OH because it releases one hydrogen, so OH negative and NH4 plus. With the concentration of OH, as we saw in previous examples, we can calculate the pOH of the whole solution and then determine the pH of the solution. Once again, we are in equilibrium, so we're going to have the four species in the same in the beaker or whatever we are doing this reaction. And from this one, we can calculate the pH of the solution. And the other product here is also known as a salt, but this one is a cation. So we can see that when we have a weak base, we produce a cation. When we have a weak acid, we are producing an anion. So could this salt could affect the pH of the solution? Many ions react with water. Remember that those salts are in the solution and you have water in the solution also. And remember that water was a pure liquid, is a pure liquid, so the concentration is pretty high. That's why you're not include that in the equilibrium constant. So some of those ions that are produced, that are the salts, could react with water and create H positive or H negative, create protons or hydroxide ions. So the reaction with water is often called the hydrolysis. So the hydrolysis basically is those molecules of water reacting with these ions. To determine whether a salt is an acid or a base, you need to look at the cation and anion separately. Okay, so you're gonna in one reaction you're gonna look for that salt and evaluate if it's a cation and an anion or an anion. The cation can be acidic or neutral, and the anion can be acidic, basic, or neutral. Okay, so let's talk about the anions. The anions of strong acids are neutral. For example, chlorine will not react with water, so OH can't be formed. Okay, so when you use a strong acid, remember that it dissociates completely, and because of that, that chlorine is not going to react with water to produce against HCl because HCl is really strong. Now, when we have anions of weak acids or conjugated bases, so they create OH in water because that conjugated base is going to react with water, and because it's a base, the base is going to produce OH. So that base will react with water. Remember that this was the salt of the first reaction that I showed you in the previous slide. This is acetate. So the acetate will react with a molecule of water that is in the environment, and this will create again the acetic acid, but the OH. So this OH is going to affect the pH of the solution. So when we have this anion, you're going to produce this anion is considered a basic one. So other anions are protonated anions from polyprotic acids that can be acids or bases. If the Ka is larger than Kb, the anion will be acidic. If the Kb is larger than the Ka, the anion will be basics. So what about the cations? From group 1 or group 2, metal cations are neutral. So if it's a cation from group 1 or group 2, it's going to be neutral. Polyatomic cations are typically the conjugated acid of a weak base. So as we also show in the other slide, this is the product of NH3 plus water. And this one can react again with water to produce NH3 and H3 positive. So what about the transition and post-transition metals cations? They are acidic. Why? We're going to see that in the next slide. So the transition and post-transition metals that we have in the middle of a periodic table, all of those cations are going to be acidic. And this is why. The transition and post-transition metals form hydrated cations. So that metal is going to bind molecules of water around it. As we can see here, this is iron, and you can see a molecule of water that is bind to this cation, and also this other water is bind to this cation, and also this one. And now this bond is gonna weak this other bond of hydrogen and oxygen, making this hydrogen more vulnerable to be removed by a base. So that's why the transition and post-transition metal increase the acidity of water. So the water attached to the metal is more acidic than free water molecules, making the hydrated ions acidic. So when we have a complex of transition or post-transition metals, those are considered acidics, okay? Because the molecules of water that are going to be bind to those um, metals, those hydrogens are going to be really, really acidic. Here we have a table of different acid dissociation constant for metal cations. And we can see here that this is increasing going down. So we have iron, zinc, nickel, and all the other metals, and the Ka for each one. So salt solutions, acidic, basic, or neutral. So group 1 and 2, the metal cation with an ion of a strong acid, they are going to be neutral. If it's from group 1 and 2, the metal cation with an anion of a weak acid is going to be basic. The transition, post-transition metals cation or polyatomic cations with anions of a strong acid, they're going to be also acidic, like the cation. And the transition, post-transitional metal cations or polyatomic cations with an ion of a weak acid, you need to compare the constant, the acid dissociation constant and the basic dissociation constant, and whichever is greater dictates what. So the acid strength could be affected by several factors. Number one, the HA bond must be polarized with the delta positive on the H atom and a delta negative on the A atom. So as we mentioned before, this is a covalent polarized bond. Okay, and as higher the difference in electronegativity, that would make that bond more polar, and that hydrogen must it will be more easy to be removed. The bond strength. The weaker the bonds can be broken more easily, and this will make the acid stronger. So we somehow we can decrease the strength of that bond, that will make that hydrogen more acidic. And the third is the stability of the anion that is going to be produced. Because remember that when you remove a proton, you're going to remove a positive charge, so you will have a negative charge that will be produced. And as more stable as more you can stabilize that negative charge, it will be more easy to remove that hydrogen. So the stability of the anion, more stable anion means stronger acid. So it's really important also the stability of that anion that you're going to produce when you're removing the hydrogen. We also have binary acids. Binary acids consist of hydrogen and one other element. Within a group, HA, bond strength is generally the most important factor. Within a period, bond polarity is the most important factor to determine the acid strength. So, in a period, the acid strength will increase from left to right, and in a group, the acid strength will increase from the top to the bottom. So this basically is a stronger acid in the binary acid groups. Now, to finish this model, we're going to talk about the Lewis acid-base chemistry. Lewis acids are electron pairs acceptors, and Lewis bases are electron pair donors. So at the beginning of the model, we talk about the Lewis and about the Arrhenius or Bronsted-Lowry acid or base compounds, and we were looking about what happened with the hydrogen. Here, with the Lewis acid base, the concept is to look what happened to the electron pairs. If that species accepted those electrons, or if that species is the one that is given the electron pair. Okay, so if that species received the electron pairs, that is known as a Lewis acid. If that species is given or is donating those electron pairs, it is known as the Lewis base. So all Bronsted-Lowry acids and bases are also called Lewis and acids and bases. There are compounds which do not meet the Bronsted-Lowry definition, which meet the Lewis definition. So let's see the following example. So here we have ammonia reacting with an acid. As we can see here, the unpaired electrons here receive that hydrogen. So this is a definition of a Bronsted-Lowry base, because Bronsted-Lowry established that the base is the one that accepts the proton. So here, the ammonium is accepting the proton, so that's why this is a base considered by the Bronsted and Lowry rules. But let's see the following example. Here, we don't have any acidic protons that could be transferred. Here we can see that the electron pairs of nitrogen is basically making a bond within the boron. Okay, so here we are transferring electrons. So Lewis established that the species that is given is donating those electrons is the Lewis base, and the species that is receiving those electrons is called the Lewis acid. So in the Lewis perspective, he's looking for the what happened with the electrons. Okay, so if the electrons the species receive or donates those electrons, the species that donates the electron is called the Lewis base, and the species that receive the electron is called the Lewis acid.